Localization with deep neural networks using ray tracing simulations by Udita and Lloyd Curtis. Here is a brief overview of our presentation. We'll cover the background and motivation, previous works and contributions, provide a neural network breakdown, discuss both of our approaches, and end with a brief conclusion. Localization is the process of determining a user equipment's location within the network. It helps in quick beamforming, which increases capacity. It uses channel parameters such as angle of arrival, which is also known as direction of arrival, angle of departure, received signal strength, and delay, which is also known as time of arrival. There are two different path types. There is line of sight and non-line of sight. Deep neural network is a machine learning technique with multiple hidden layers between its input and output. We're using the deep neural network because present algorithms are complex and time consuming. An example of a present algorithm is one which utilizes RSRP and timing advance to develop a signature which represents a location. With the deep neural network, we can make the localization process faster and less complex. Given a ray tracing simulation, we design a deep neural network to provide the location of a UE through supervised learning. We consider two approaches. In our first approach, we consider channel parameters like AOA, delay, and RSS. This approach uses three different combinations of multipath components to observe which combination provides a predicted output that is closest to the desired output, with that output being the UE's location in the form of X and Y coordinates. Then we optimize the neural network using a fixed number of hidden layers. Optimization involves testing which combination of hidden layer nodes, activation function, and learning rate provide the most efficient neural network. Also, in this approach, we assume a fixed number of multipath components for each user. However, in reality, the number of multipath components will differ for each user. In approach 2, we use the deep MIMO dataset, which captures channel dependence on environmental factors such as building geometry and building materials, and as well as transmitter and receiver location, while providing a more dynamic dataset for the machine learning algorithm. It is independent of the number of multipaths, and in this approach, the number of channels is equal to the number of antennas. Here's a list of previous work and contributions. In the first paper, we can see how the location of the eNode B affects the localization of a node. In our case, we're using a single eNode B. In the second paper, it discusses how time of arrival or delay helps in localization and why we should include it as an input feature. In the paper Channel Estimation and Vehicular Communication, it shows which parameters are vital for channel estimation, and then non-line of sight identification for ultra-wideband localization. It discusses the effects of non-line of sight on localization on ultra-wide bands. In the next paper, it discusses the application of how deep neural networks can be used to solve complex issues in wireless communication, like classification of different type of nodes. And then in prediction of channel features using neural networks, it discusses the combination of different features like angle of arrival and angle of departure to discover unknown features at the UE through the use of a neural network with a fixed number of hidden layers. And lastly, in the prediction of massive MIMO channel characteristics using convolutional neural networks, it discusses the use of a feed-forward network to map the relationship between channel characteristics and geographical location with millimeter wave channels. Here's a breakdown of our deep neural network. First, we have the input, which is a number of inputs will change depending upon the number of features used for training a neural network. 3 multipath components are considered for each case, and the number of inputs will be 3 times the number of features. For our hidden layers, we consider 2 within our project. The number of nodes in each hidden layer has been optimized using optimization hyperparameters in MATLAB. And for our output, in each case, the X and Y coordinates are the outputs of our neural network. In scenario one, um, all users are assumed to be lying in the same plane, hence the Z coordinates are not considered. Here is a visual of our deep neural network. As you can see, potential inputs, the hidden layers, and the considered outputs. Our approach. In approach one, we'll train the neural network using 3 different combinations of channel parameters. The first combination is usually only azimuthal angle of arrival. The second approach is using azimuthal angle of arrival and received signal strength. And the third approach is using azimuthal angle of arrival, received signal strength, and delay. In approach 2, we train the neural network using channel response. The result in this case can be improved by using feature transform technique. For approach 1, we use a ray tracing scenario created in Wireless Insite by Chaitin. We consider 2 frequencies, one being 5 gigahertz with a 100 megahertz bandwidth, and the other being 28 gigahertz with a 500 megahertz bandwidth. The spacing between UAs is 1 meter. The antenna type is half-wave dipole. The base station is denoted as transceivers 1. The UEs will be receiver grid 3, which encompasses 540 nodes, and receiver grid 2, which encompasses 990 nodes.
Here are the functions which we have used in MATLAB to train the neural network and process the data. So in the first function, data processing, we are getting raw data from Wireless Insite, which includes all the possible parameters. It gives all the possible channel features. We have taken only receipt signal strength and azimuthal angle from direction of arrival file, and delay, that is TOA, from time of arrival files. For location, we have used path gain file. Only X and Y coordinates are used for location since all the users are in the same plane. Next, coming into the multi-layer function. This function gets the data and train the network in using feed-forward neural network. The hyperparameter optimization is done by the loss calculation function, where the number of nodes in hidden layers, learning rate, activation function is being optimized using Bayesian optimization technique. Then all the data are considered to train the neural network with optimized parameters. In the CDF function, this function gives the comparison between 3 different combinations in terms of CDF. As we can see, considering only AOA, that is angle of arrival, in some part of the figure, the neural network cannot predict the location correctly because there will be multiple users having same AOA. When RSS is considered along with AOA, it's giving better result. Considering of delay, that is TOA, along with RSS and AOA, it does not improve the result as such. RSS is somewhat related to TOA. Like RSS is in terms of power and TOA is in terms of time. While in case of non-line of sight, only DOA cannot predict the location at all. As we can see, many predicted points are overlapping because they are having same DOA. When RSS is using along with DOA as input, the neural network performed little better since it can differentiate the users with 2 parameters. Adding delay with other 2 add another degree of freedom. So the neural network can predict the location better. As we are considering 3 multipath components in this project, delay and RSS of different MPC, that is multipath component, help the neural network to train itself little better. If we increase the number of multipath components, the result can come out to be better than this one. The CDF calls in the next slide will give more intuitive interpretation of the result. So in the CDF car, x-axis is the amount of error and y-axis is how much percentage of users are having a particular error. For line of sight, the blue curve is showing that when DOA is the only input, approximately 90% times the error is within 10 to the power of 0, that is 1 meter, which is our spacing between users. Now the curves for DOA plus RSS and DOA and RSS plus delay is almost same as we discussed in the previous slide. Here, approximately 90% of the time, the error is within 10 to the power of minus 1, that is 0.1 meter, which is quite acceptable. But for non-line of sight, the error is greater. The curve is more flattened here. For DOA plus RSS plus delay curve, 30% of the time the error is within 0.1 meter. But in some cases, the error is more than 1 meter. As mentioned earlier, increasing number of multipath components, better result can be obtained. We repeated the same experiment with the data at 28 GHz just to check how the neural network performs in millimeter wave frequencies. The result has been come out to be better, the reason being dependent on the neural network parameters, with respect to the number of features, the same conclusion can be drawn that DOA, RSS and delay give better result than only DOA. Also, we can observe that adding delay with DOA and RSS does not make huge difference for line of sight. For non-line of sight, considering delay along with RSS and DOA is giving better result, we will see the comparison in the next slide. For line of sight, approximately 90% of the time, the maximum error is within 0.1, even for DOA, considering DOA only. For non-line of sight, considering DOA plus RSS plus delay, approximately 90% of the time, error is within 1 meter. This is a glimpse of optimization table for the neural network parameters. The neural network has been optimized using 30 different combinations. Error has been considered using mean square error. After obtaining the best combination, neural network has been trained with those parameters. This is a table which shows the best hyperparameters found by the Bayesian optimization technique for different cases. For example, for line of sight data at 28 GHz, while considering DOA only as input, the best hyperparameters are found to be 50 number of nodes in hidden layer 1, 41 number of nodes in hidden layer 2, and the learning rate to be 0.97691 and activation function to be tan C. As we discussed in the introduction part, in reality, users will have different number of multipath components, but the neural network mentioned previously consider fixed number of multipath components. To increase the flexibility, we took another approach to consider the channel response as input. In this case, the channel matrix will depend upon the number of antenna in a MIMO, which is quite fixed for a particular setup of base station. The data has been taken from deep MIMO dataset, which is available in the below link. We have considered only single base station, that is base station 3, as transmitter. The users between 1000 and 1025 are considered. In this paper, the spacing between the users is 20 cm. But for our setup, we have pre-processed the data a little to make the spacing 1 meter for better comparison. And the user grid 1 is considered as the receiver, which contains 185 points. Here are the functions used for approach 2. First, deep MIMO dataset generator, where we mention about which base station we are considering, number of users, number of antenna, etc. In the deep MIMO generator function, it takes the inputs from the previous function and prepare the data to calculate the channel response. The construct deep MIMO channel function calculate the channel response for each user. To make it simple, we have taken the absolute value of the channel response. In the channel function, this is the neural network which take the absolute value of the channel response as input and gives the location as output. Again, we ignored the z-axis and location since all the users are in the same plane. Loss calculation function performs the hyperparameter optimization similarly as it did in the previous neural network. The first three functions are used from the reference below. Channel and loss calculations are the two functions created by us. As we can see, the result is not at all good. This is because the absolute value of the channel response will be pretty close, since the spacing between the UVs are very small. Hence, neural network is being confused to predict the location. The problem can be solved using feature transform technique, where the input will be sparsely distributed to help the neural network to train itself efficiently. We haven't included that part in this project. That's a future direction of the project. Here is some conclusion which we can draw. Once the deep neural network is trained, it can predict the location almost immediately. We can compute the computational complexity approximately to be in the order of I into n1 plus n1 plus n1 into n2 plus n2, where I is the number of input, n1 is the number of nodes in the first hidden layer, n2 is the number of nodes in the second hidden layer. So in this project, static scenario has been considered. To make it more realistic, dynamic scenario can be considered. The performance of the neural network can also be checked using the real collected data, which is pretty difficult to get. Both the neural network can predict the location if known parameters has been inputted, as this is the supervised learning. In real life, the neural network has have semi-supervised learning technique or unsupervised technique. Thank you, and you can contact us for any further details.